Now our focus presently is to build a relation between the strain amplitude and number of cycles to failure. What we've observed was that for sure there is a relation between the strain amplitude and the stress amplitude that's going to be eventually useful, so that if the information that we have is the stress amplitude, we can still map it to a strain amplitude based on the model of the cyclic stress strain curve, and then go for still our strain-based approach to fatigue. Okay, or alternatively, if we are given the strain amplitude and we have a stress-based approach that is very good, we can still use the cyclic stress strain curve model that is in the Ramberg-Osgood format, for instance, and go for map strain amplitude to stress amplitude and go for the stress-based approach. So either way, we need a model for either stress-based or strain-based fatigue. Now we want to build a model for strain-based fatigue because in the case of stress we had the Baskin equation. Now because strain-based fatigue is mostly meant for low cycle, or that is fatigue, or that's where its strength lies, we notice first of all that in low cycle fatigue we have significant plasticity, which is, again remember, implicitly and directly captured in the Ramberg-Osgood model that relates stress amplitude to strain amplitude. Okay. So what we want to therefore do is we want to measure the plastic strain as we cyclically deform a specimen and relate it to the number of cycles to failure. So we're going to talk about not the stress life curve, but a plastic strain versus life curve. And that curve is generated based upon experimental data, of course. So again, this is going to be our life. And as usual, it works on a log scale. Now, the vertical axis is going to be the plastic portion of the alternating strain. So when we cycle the specimen, we cycle it between a max and a minimum, a positive and a negative strain with a zero mean. And a portion of that alternating strain is plastic, a portion of it is plastic. We can continuously monitor the specimen and measure the amount of plastic strain that we are applying on the stable hysteresis or the stable cyclic loading, and therefore for a given cyclic loading we have a well-defined value of the plastic alternating portion of the plastic strain, and therefore we can map it directly to number of cycles to failure. Okay, so we prescribe the strain amplitude. There is a unique plastic strain amplitude that corresponds to it, and then the cycle, the specimen fails after so many cycles. So for a given measured plastic strain amplitude, I put a dot here at the point where failure occurs. Now, the idea is the plastic strains, of course, are larger if the stresses are larger. How do I see that? Well, I can see it directly from the Ramberg-Osgood model of the cyclic stress strain curve. If this is larger, stress is larger. If the stresses are larger, already I have an intuition that the life is going to be less. Or in other words, if we decrease the plastic strain or we decrease the stress amplitude, then the life is going to get longer. So then we collect data, and here I'm drawing that data in a highly idealized form. We collect the data, and it turns out that that data lies almost unaligned. But we have to remember that convention dictates that the strain axis is also plotted on the log scale, because that's where, if I see a line, I know that there should be some power relation between the two axes, the variables that govern the two axes. So just to give you an idea about the orders of magnitude here, number of cycles can start from 10 and go all the way up to, say, 10 to the 4 and beyond. Now I know that the transition from low to high cycle is going to occur somewhere in there, but certainly I know that somewhere to the left of it definitely lies in the low cycle regime, and beyond is somewhere where high cycle is going to start. But I know that this data for sure has contributions. In fact, a significant portion of it has contributions from low cycle regime. So that's the data that I collect, and the strains, plastic strains that are imposed could be as large as 1%, which is quite a bit of plastic strain. Perhaps they could be even larger. Okay, so we go ahead and this is our data, and we fit a model to it. Okay. So this is our fit, and that fit is associated with a model. Now that on a log-to-log, log-log scale, I see a line suggests that that relation is of the power form, and so we know that epsilon PA, the plastic portion of the alternating strain, is associated with number of cycles to failure through a power relation. Following the Basquin form, we're gonna write it in this fashion. Okay. Now notice that we are assuming zero mean, so I could have, or I might as well here throw in a R here to indicate that this is associated with completely reverse loading, but presently we are going to skip that. But just don't forget that the mean strain and hence mean stress is assumed to be zero presently. So this is the data, or this is the relation that is motivated by experimental data, and it's a good model. Now, let me just correct quickly that this exponent should have been not B, but rather C. Now, again, we remember that just like in the Basquin equation, the slope of the line is negative, and therefore the coefficient C is less than 0. So, because we have negative slope on log-log scale. All right. Now, this relation was proposed by Coffin, two researchers, Coffin and Manson, in the 1950s. Now, we're not going to refer to this as the Coffin-Manson equation. It's what we're going to refer to as the Coffin-Manson equation is going to be slightly more generalized, but this is the cornerstone of low cycle fatigue. Low cycle fatigue is where significant plasticity occurs, and so the idea is that, well, why don't we monitor the plastic strains? Of course, I'm referring to the alternating portions only, and map it to number of cycles to failure. That's a very clever approach, and it turns out that's an approach that is very amenable to modeling because the data is rather supportive of such a model. Okay, now at this point you may, however, remember also the Basquin equation argument, and in the Basquin equation argument, what we had said that, well, why do we have a factor of 2 here? Because 2NF is the number of load reversals. And if failure occurs at the first load reversal, I put a 1 there, and so this thing becomes 1. Failure occurs at epsilon PA is equal to epsilon prime F. So in other words, one direction of loading, if it leads to failure, it occurs with epsilon A approximately equal to epsilon prime F, and so the idea is epsilon prime F probably has to do with something that's associated with the uniaxial stress-strain behavior, or it can be somehow motivated by some failure strain. And it turns out, indeed, just like for the Basquin equation where sigma prime F was associated with the true fracture stress, in this case, it turns out by the same argument that I've outlined that epsilon prime F is associated with the true fracture strain. It does make sense that it's associated with the uniaxial stress-strain curve failure value, because if failure occurs at the very first cycle, then it's almost like, or in fact even the first half cycle, then it makes sense that epsilon prime F should be associated with that failure value, and indeed experiments are supportive of that observation. Okay, so epsilon prime f, if we don't know exactly what it is, we can approximate it as being the true fracture strain. Of course, there's ample experimental data that's going to tell us what epsilon prime f should be for strain-based fatigue applications. Okay, so but remember, our goal is not to relate the plastic strain amplitude to number of cycles to failure. It's nice that we have such a good relation, but it's hard to measure the plastic strain. Now, measuring the strain amplitude is easier. And that's why we want to find a direct relation between the strain amplitude and number of cycles to failure. But plastic strain is just a portion of the total strain amplitude. There is also the elastic portion. So unless I know how that varies or how that is associated with the number of cycles, then I cannot have a model that I am aiming for. This is just one piece of the puzzle. So therefore, let us also try to measure the elastic strains. And in fact, if in an experiment I was able to measure this, well, from the total strain I can extract it, subtract it, and generate a plot for elastic strain amplitude versus number of cycles to failure. Okay, so the specimen is subjected to epsilon A. This is the major thing, and I can measure the plastic contribution to that amplitude and then subtract that from this and find the elastic strain contribution to this amplitude. Either way, the specimen is going to fail for this amplitude at a given number of cycles. So now, again, we're gonna plot on a log-log scale number of cycles versus the strain amplitude. So it's the same specimens, right? So here, the values that we measure, of course, can be different, but let's assign the same range. Okay, so we do the test with the specimen and we measure the plastic portion of the strain, elastic portion of the strain, amplitude, and then failure occurs at this many cycles, at that many cycles, the same number of cycles. And it turns out with that strain amplitude, this is the plastic strain amplitude and this is the elastic strain amplitude. Okay. Again, we know that if you want to go up to a higher number of cycles, the elastic strain amplitude also needs to be less. How do I know that? Well, because from the Ramberg-Osgood model, if we have a smaller epsilon EA, then stress amplitude decreases, and I know intuitively that smaller stress amplitudes lead to larger lives. So we collect the data for all of those points as we did earlier and just do a different map, this time elastic strain versus life. And again, let me idealize the curve. This is what we end up with. Well, it's the same set of data, so let me put roughly the same number of points. Okay, so then we go ahead and we again fit a line through this. Okay, so notice again that we have the same, essentially the same range where somewhere around low to high cycle fatigue transition is going to take place, but the data that we are collecting, it's the same experiment, it's just different portions of the total strain amplitude we're plotting here. The data is certainly having a lot of contribution from the low cycle regime where significant plasticity is taking place. Okay, so here this is the data, and now this is going to be our fit. This time the fit relates the elastic strain amplitude to the number of cycles to failure. Okay, well, On a log-log scale, again, I observe a line. So why don't I put it almost in the Basquin form with values alpha as a coefficient and beta as an exponent? Now, I'm going to play with this expression a little bit. So first of all, what I will do is I will multiply both sides with E, the Young's modulus. Okay. Now, when I do that, what I observe on the left is the Young's modulus times the elastic strain amplitude, and from the stable cyclic stress strain curve, I know that this is equal to simply the stress amplitude. The mean stress is 0, sigma A is Young's modulus times the elastic strain amplitude, okay? So the model says that elastic portion of the strain is on a log-log scale proportional to an F, or with a negative slope, so beta for sure is also negative, right? And now I multiply both sides with E, and I see that the stress amplitude emerges. Now, when I see the stress amplitude on the right and the life appearing as twice life on the right, I immediately remember the Basquin form. And the Basquin form said that sigma A was sigma F prime, a coefficient times an exponent, which what we called B. All right. So therefore, what I will do is now I will work on this form, and now I multiply both sides by E, and I saw E alpha, and I call that sigma F prime. Now, let's wait for a second. It's not necessarily the same sigma F prime that we value-wise that we saw in the Basquin equation. All we're saying is that on a log-log scale, epsilon EA is associated with an F. It's a line, negative slope. And I multiply both sides with E. On the left, I see stress amplitude. On the right, I see a EF coefficient, E alpha coefficient, and I called it sigma F prime. It's a coefficient. I just happen to call it sigma F prime. And there's an exponent. Why don't I call it B? And once I do that, I'm going to divide both sides by E again. And we are going to write that epsilon EA is equal to E alpha over E, or sigma F prime over E, 2NF to the power B. Okay? And therefore, we are going to essentially propose a relation that is motivated by the Basquin form. It is motivated in the sense that I saw a coefficient that's relating life to stress amplitude, and I called it sigma F prime. But really, I'm concerned with this elastic strain amplitude, so I went ahead and divided the stress by E, or this coefficient by E. Instead of calling it alpha, I called the whole thing, just retained it, sigma F prime over E is what I retained. And the exponent, instead of some arbitrary thing beta, I called it B to remind me of the Basquin form, because that seems to somehow apply in this case, at least form-wise as well. There's a linear relation between stress and life, and therefore elastic portion of the strain, amplitude, and life. All right, so that is what I have. Now, having said this, again I highlight the data that comes into this fit, into the determination of alpha and beta, or instead of beta we wrote B, and instead of alpha we wrote sigma F prime over E. Those are, so let's write that, so this is alpha and this is beta really. The values of sigma F prime and B, they are associated with this data, and as such, eventually their values might differ from the values that we had for high cycle fatigue, because there the data came from number of cycles to failure that were much larger. And indeed, eventually when you look in the book for values of sigma F prime and B that are applicable to the strain-based fatigue, that is meant mostly for low cycle fatigue, their values might be different than the values that we, and are sometimes different than the values that we saw earlier for the high cycle fatigue. All right, so now these are the two portions of the total strain, and now I'm just going to combine them and generate a final relation between the strain amplitude and number of cycles to failure.